So, welcome back. Let us consider another numerical problem, slightly higher order compared to the previous problem. For the beam loaded shown in figure, draw shear force diagram and bending moment diagram marking the values at salient points. It is again a single overhanging beam subjected to a uniformly distributed load between supports of intensity 3 kilonewton per meter. 2 point loads are acting in between the supports 5 kilonewton, 3 kilonewton, and another point load acting at the overhanged free portion. Salient points are not marked. Let us mark the salient points to our convenience. As usual, let us give A and B to the supports. Next point is C at point load 5 kilonewton, D and E. Mark the support reactions at A and B, or A or B. Now let us calculate support reactions. State the reactions. Let RA and RB be the support reactions at A and B respectively. Now apply equilibrium condition. For equilibrium, first apply moment equilibrium condition. We will apply moment equilibrium condition at point A so that RA becomes 0. The another unknown reaction RB can be calculated in a single step. Applying sigma m about A is equal to 0, that is, consider all the loads acting in the beam including the support reactions. Purposefully we have taken moment at point A to make this RA 0. So, the another unknown RB can be calculated in a single step. As RA will not create any moment about point A, that we are not going to write to avoid confusion. And the remaining moments due to the remaining loads we are going to write along with their sign conventions. First, let us decide the loads which are creating clockwise moment and anti-clockwise moment separately. The point load 5 kilonewton acting at point C will try to rotate the beam in the clockwise direction, in the downward clockwise direction, positive. This 3 kilonewton, again it is rotating the beam in the downward clockwise direction, positive. This uniformly distributed load, if you convert into point load, 3 into 4.5, a point load, it is acting at the midspan of the UDL, and this point load of UDL is also rotate the beam in the clockwise direction, positive. A reaction RB acting at point B will rotate the beam in the upward anti-clockwise direction, negative. Lastly, the 2 kilonewton load acting at the free end of the overhanged portion try to rotate the beam in the clockwise direction, positive. So, totally there are 1 point load 5 kilonewton, 2 point load 3 kilonewton, UDL 3 and support reaction 4, and lastly point load 5. So, we have to consider moment due to all these 5 loads by considering their sign conventions. We should be very careful in deciding the sign convention. There is no confusion here. If you treat clockwise positive, automatically anti-clockwise will be negative. And we are not considering now, as we stated already, RA, because it is not creating any moment, we are not writing. Let us consider the forces one by one. If I consider the force 5 kilonewton first, and this 5 kilonewton will create a clockwise movement about point A, positive, 5 into 1.5. Next 3 kilonewton, that's also creating clockwise movement about point A, again positive, plus 3 into the perpendicular distance is 1.5 plus 1.5, 3 meters. Next, after considering these 2 point loads, let us consider this UDL. Here we consider, again for easy calculation purpose, we have to consider the entire UDL in a single shot. The intensity is same everywhere here from A to B. It is same from A to C, C to D, D to B. So let us consider the entire UDL in a single shot, and that UDL, point load of UDL is also creating a clockwise movement, hence positive, plus 3 into, convert this UDL to point load, 3 into 4.5. This is point load, and it is acting at the midspan into 4.5 by 2. Next, consider this RB. RB will rotate the beam in the counterclockwise direction, hence it is negative, minus RB into 4.5, perpendicular distance RB into 4.5. Lastly, 2 kilonewton load will create the clockwise movement about point A, plus 2 into, so perpendicular distance here from here to here is 4.5 plus 2.4, 4.5 plus 2.4, it is 6.9. 2 into, it is 2 into total distance, 6.9, that is equal to 0. So there are 1, 2, 3, 4, 5, 6 loads. Moment due to RA we have not considered, remaining is 5, 1, 2, 3, 4, 5. So moment due to all the 5 forces we have considered. Now, so if you calculate, solve this expression, you will get RB is equal to 13.48. Now, let us apply the another equilibrium condition, namely the vertical force equilibrium condition, and applying sigma V is equal to 0. That is, we will consider all the forces here, including support reactions and sign conventions. Proceed from left hand to right hand side. RA acting in the upward direction positive, minus 5 kilonewton, minus 3 kilonewton, minus 3 into 4.5 UDL. RA as it is we considered 5 kilonewton acting in the downward direction negative, 3 kilonewton load acting in the downward direction negative, minus this UDL 3 into 4.5 acting in the downward direction we have considered. Next, plus RB acting in the upward direction. Lastly, a point load acting at point E acting in the downward direction, minus 2, that is equal to 0. So here we consider only 5 forces for the moment, because RA will not create any moment about point A, whereas we have to consider only forces. We considered all the 6 forces, 1, 2, 3, 4, 5, 6. So RA plus RB is equal to RA plus RB is equal to 23.5. Therefore, RA is equal to 23.5 minus RB, that is RA is equal to 23.5 minus 13.48, that is equal to 10.02 kilonewton. If you calculate support reaction, it is the foundation is laid for drawing shear force and bending moment diagram. The correct calculation of support reactions are very, very important. We should be very, very careful to calculate support reactions. So let us mark the calculated support reactions here on the loading diagram. 10.02 kilonewton RA, then RB is equal to 13.48. So this is our completed loading diagram. So knowing the completed loading diagram, we can comfortably draw the shear force diagram. For that, produce the salient points in the downward direction by means of dotted line. Let us draw the reference line to draw the shear force diagram. On the reference line, shear force values are 0. Proceed in the direction of forces acting. At point A, there is a support reaction, it is a point load acting in the upward direction, positive above reference line. The value is 10.02 kilonewton. Between A and C, there is a UDL, and this problem will give us better practice. We already taken one problem of this kind. Here there are 2 point loads between the UDL. Between A and C, there is a UDL. Consider this UDL separately and draw shear force diagram for this portion AC. So 3 into 1.5. The variation of shear force diagram for UDL is a parabola. 3 into 1.5 is 4.5. Come down by 4.5, linearly by 4.5. So 10.02 minus 4.5, it is 5.52 kilonewton, remaining value. At point C, there is a point load acting in the downward direction. We know the variation of shear force diagram for a point load. It is a vertical line. It will come down vertically by 5 kilonewton. Remaining value is 0.52 kilonewton. Next, between C and D again there is a UDL of same intensity 3 kilonewton per meter. The span length between C and D 1.5 meter. 3 into 1.5 again 4.5 kilonewton. We have to come down linearly by 4.5 kilonewton, and as a result it will forcibly cross the reference line. So below reference line it will come down by 0.52 minus 4.5, 3.98 kilonewton. At point D, there is a point load again acting in downward direction, come down by 3 kilonewton. It is 6.98. We come down directly because variation of shear force diagram for a point load, it is a vertical line. Between D and B, again there is a uniformly distributed load. Again span is 1.5 meter, intensity is same 3 kilonewton per meter. 3 into 1.5, 4.5 kilonewton point load. It will come down linearly by 4.5. We already came down by 6.98. Further we are going down by 4.5. Totally it is 11.48 kilonewton. At point B, there is support reaction, point load acting in the upward direction. We had come down by 11.48 kilonewton below reference line. Here we have to move by 13.48 kilonewton, go up by 13.48 kilonewton. It will forcibly cross the reference line, and above reference line it will move by 2 kilonewton. Between B and E, no load. The variation of shear force diagram for no load condition, horizontal line. Here also it is 2 kilonewton. When we come to point E, there is a point load acting in the downward direction. Come down vertically, meet with the reference line. Shear force diagram changed its sign from positive to negative, again negative to positive. Diagram changed its sign from positive to negative at an unknown point. Let us mark this point as, say, F. Let this F acts at a distance of x from left support and mark this F also on the loading diagram. Along with the distance from A point. Produce point F also in the downward direction. It helps us to locate the bending moment calculated. We know shear force at various salient points including point F. Shear force at point F is 0. We can mark the values here. Write down the shear force values at various salient points. Shear force at A, shear force at A, comma FA is equal to 10.02 kilonewton. Shear force at C, FC, it is 5.52 and 0.52 above reference line positive. Shear force at point F, FF is equal to 0 on the reference line. Next, shear force at point D, FD, it is, there are two values, both are negative values, minus 3.92 kilonewton and 6.98 kilonewton. Sorry, 3.98, okay. 3.98 and 6.98 kilonewton. Next, shear force at point B, FB, minus 11.48 kilonewton and 2 kilonewton. Lastly, shear force at point E, FE is equal to 2 kilonewton and 0. Always we have to proceed in the order. To draw the shear force diagram, we started from point A, moved up, then draw the shear force diagram from between A and C linearly. Then there is a point load, come down. At point C there are two values because of this UDL and point load. Again between C and D, shear force diagram changed its sign at point F. That value we have marked. At point D again we have marked 2 points. First is 3.98 and 6.98. At point B again there are two values. First it is minus 11.48 and 2 kilonewton. Lastly it is 2 kilonewton. In the order we have drawn, and the same order we have marked the shear force values. This is our shear force diagram. Complete shear force diagram. Now, to draw the bending moment diagram, we need to calculate bending moment values at various salient points. Bending moment at A, comma, MA by considering forces to the left hand side, no forces, no bending moment, A. Next, bending moment at C, MC again by considering forces to the left hand side. To the left of C, 10.02 kilonewton point load in the form of reaction. It is creating a clockwise moment about point C positive, and UDL between A and C, it is creating a anti-clockwise moment negative. 10.02 into 1.5 minus 3 into 1.5, it is a point load into 1.5 by 2. So, this is the bending moment about point C. 11.65 kilonewton meter. Now, shear force diagram changed its sign from positive to negative at an unknown point F, and we need bending moment at point F. To calculate bending moment at point F, let us first calculate the distance x of F from left support. For that, take out the portion of the beam to the left of point F, and that helps us in calculating both x as well as the bending moment at point F. Point F, a support reaction 10.02 kilonewton, and UDL is acting throughout of 3 kilonewton per meter. A point load is acting 5 kilonewton, and the distance is 1.5 meter from left support, and the distance of UDL point F from left support is x. This is point A, C. From the shear force diagram, it is observed that shear force at point F is 0. Let us write shear force at point F. Let us write expression for shear force at point F by considering forces to the left of the point F, because we have considered this distance x from the left hand side. Even we can show this distance x to nearby point. Even from here to here you can show x, or from here to here you can show x, or from here to here. Accordingly, we will get the value of x. Again, this is simpler. That's what I consider the x to the left of the point. When we consider this distance x to the left of the point, obviously we have to consider forces to left of point F only to write expression for shear force. We know shear force at point F is 0. Write expression for shear force at point F by considering forces to the left of the point F and equate it to 0, you will get x value. Shear force at F, comma, FF by considering forces to left hand side is equal to 0. That is, again it is a practice for us. In the last problem also we written expression for shear force. Here also we are writing expression for shear force. In the course we will learn how to calculate shear force. Shear force at F. There are three forces to the left of F. One is point load 10.02 kilonewton acting in the upward direction. Another one is again 5 kilonewton acting in the downward direction. UDL between A and F. We want only load. We don't want any distance. Load and their direction. Here to the left of the point, treat upward as positive and automatically downward will be negative. That is 10.02 it is an upward force positive. Next 5 kilonewton acting to the left of the point, downward is negative, minus 5. Again this UDL, convert this UDL to a point load, and this converted point UDL point load also acting in the downward direction, hence negative, minus 3 into x, that is equal to 0. Solving this, you will get x is equal to 1.67 meter. Now we can comfortably calculate bending moment at point F. So bending moment at point F, comma MF, again by considering forces to the left hand side. Again we have to consider these three loads. This 10.02 support reaction will create a clockwise movement about point F. 5 kilonewton point load will create anti-clockwise movement about point F. This UDL is also creating anti-clockwise movement about point F. First consider this the support reaction, 10.02 into 1.67 perpendicular distance. Next, this 5 kilonewton will create anti-clockwise moment. To the left of the point, consider anti-clockwise negative, minus 5 into this distance, 1.5 plus 1.5, it is 1.5. Here distance is 1.67, means point, it is 0.173. So total distance is 1.67. From here to here it is 1.5, 1.5 means it is x. So 1.67 minus 1.5, it is 0.173. Next consider this UDL. This UDL is also creating anti-clockwise moment about point F, minus 3 into 1.67. Now let us consider the full distance x. Minus 3, minus because point load of this UDL is also creating anti-clockwise moment, minus 3 into x means 1.67, this is point load, into 1.67 divided by 2. So we have considered all the three loads here. Support reaction is creating a clockwise moment positive, this point load 5 kilonewton creating anti-clockwise moment negative, and this UDL is also creating anti-clockwise moment negative. So this MF works out to be 11.72 kilonewton meter. After calculating bending moment at point F, let us calculate bending moment at point D. MD. Here we can consider forces to the left of the point D or to the right of the point D. The sides, both the sides we have point loads, 2 point loads, both the sides we have one on UDL. Let us consider the side to the right hand side, MD. To right side of D, there is UDL here between D and B, a point load in the form of support reaction, another point load. Left we consider clockwise as positive, to the right side it is anti-clockwise positive, clockwise negative. To right of D, at point D of course there is a point load 3 kilonewton, and this 3 kilonewton will not create any moment at point D, and hence we are not considering the 3 kilonewton. Let us consider UDL. This 3 kilonewton per meter UDL creating the clockwise moment about point D. Clockwise means it will try to bend the beam in the upward direction. It is creating a hogging bending moment. Hogging bending moment is negative. So minus or else our assumed sign conventions. To the left of the point treat clockwise positive, anti-clockwise negative. To the right of the point treat anti-clockwise positive and clockwise negative. And in the beginning we have assumed that sagging bending moment as positive and hogging bending moment as negative. At point D, MD, minus bending moment due to this 3 kilonewton, it is minus 3 into 1.5 this is point load into 1.5 by 2. 3 into 1.5 point load, it is acting here, and that it is acting at the midspan 1.5 by 2. Next, this 13.48 kilonewton point load support reaction will create the anti-clockwise moment about point D, and this anti-clockwise moment will try to bend the beam in the downward direction, sagging bending moment, that is positive, plus 13.48 into perpendicular distance 1.5 meter from D to B, next this 2 kilonewton will try to bend the beam in the upward direction, though it is creating clockwise moment, it will try to bend the beam in the upward direction, hogging minus 2 into the perpendicular distance is 2 into 1.5 plus 2.4, 1.5 2.4 it is 3.9. This works out to be 9.045 kilonewton meter. Now let us come to point B. At point B, we consider to the right hand side, obviously there is a point load here at point B in the form of support reaction, and this support reaction will not create any moment at point B, we are not considering that, and this will create this point load acting at the free end will create a clockwise moment, and this clockwise moment will bend the beam in the upward direction, hogging moment negative. So bending moment at point B, MB, by considering forces to the right hand side, and RB we are not considering, bending moment due to that 2 kilonewton acting at the free end minus 2 into 2.4, that is equal to 4 minus 4.8 kilonewton meter. Coming to point E, at point E, if you consider forces to the right hand side, no forces, no bending moment. Even if we consider forces to the left hand side also, we will get the 0. So after calculating bending moments at various salient points, we can locate the values on the reference dotted line we have drawn already. Let us draw the horizontal reference line. Bending moment at point A 0, bending moment at C it is 11.65, 11.65 kilonewton meter. Bending moment at point F it is 11.72, 11.72. Next bending moment at point D 9.04, 9.045 kilonewton meter. Bending moment at point P is minus 4.8, 4.8 kilonewton meter. Lastly, bending moment at point E is 0. We can comfortably draw the bending moment diagram knowing the values at various salient points, and we know the variation of bending moment diagram for various loading condition. Between A and C there is UDL, the variation is parabola. At point C there is a point load, no change in bending moment diagram. Between C and F also there is a UDL parabola. Between F and D there is again UDL parabola. D and B UDL is there, this is again a parabola. Between B and E also there is no load, means variation is a linear line. Straight linear line. Bending moment diagram changed its sign positive to negative at unknown point. Let us mark this point again as G. Produce this G to the loading diagram, mark it as Y. From the nearby right support, you can mark it as bending moment diagram. We can comfortably locate the point of contra flexure, means calculating Y. If you calculate Y, that is the location of contra flexure from nearby support. Now, to locate point of contra flexure, we know bending moment at point G. Bending moment at point G is equal to 0. Consider forces to the left of the point G or to the right of the point G. Write expression for bending moment at point G and equate it to 0, you will get the Y. Here to avoid confusion, we can take out the portion of the beam to the right of point G. A 2 kilonewton point load, a 13.48 kilonewton support reaction. UDL is acting between G and B. The intensity of UDL is 3 kilonewton per meter. The distance we considered is Y from G to B, and here it is 2.4 meter between B and E. We know bending moment at point G. Bending moment at point G is 0. Bending moment at G, comma, mg by considering forces to right hand side is equal to 0. To left hand side also 0, both side. But here we have considered forces to the right hand side. Since we have marked this distance y from nearby right support, we have to consider forces to the right hand side. That is, so as usual, this 3 kilonewton creating a clockwise moment. To the right of the point, clockwise will be negative, minus 3 into y into y by 2. 3 into y, the point load, and its point of application is y by 2. Next, this 13.48 kilonewton will create the anti-clockwise moment. To the right of the point, anti-clockwise positive, plus 13.48 into y. Lastly, this 2 kilonewton point load acting at the free end E will create the clockwise moment. clockwise to the right is negative, minus 2 into y plus 2.4, and that is equal to 0. That is minus 3 y square by 2 plus 13.48 y minus 2y minus 4.8, that is equal to 0. So here we will come across a quadratic equation. If we solve this quadratic equation, we will get the y value. Of course, we get two possible values of y's, and the y calculated should be less than 1.5. Y calculated should be less than 1 because the total length of the span between D and B itself is 1.5, and y should be very much smaller than 1.5. If the y value is more than 1.5, worked out value of y is more than 1.5, it is irrelevant value. So solving will get y is equal to 0.42 meters. So like this we can draw shear force and bending moment diagram, marking all the salient points, and also we can have the positive values of bending moment. Then the point of contra-flexure can be located. The combination of loads with the combination of UDL and point load. In the previous problem, we have considered a simple UDL, and between the UDL one point load was acting. And in this problem, purposefully we have taken to enhance our the concept by considering 2 point loads between the UDL. So with this discussion, let us wind up this class, and for more discussions we will meet the next class. Thank you.